Hello again. In this lecture we will take a short look at one reason for shifting in another way than for minimizing fuel consumption. This is the gear shift strategy we have discussed earlier, and it focuses on minimizing fuel consumption. Since it allows the vehicle to use the full operating range of the powertrain, in fact it also provides the maximum performance that the powertrain can provide. So if we just look at steady-state driving situation, there is no conflict between the most fuel-efficient strategy and one which can provide full performance. This strategy managed to do both. However, there is one shortcoming. Gear shift takes time, so every time the transmission needs to shift down in order to provide the required force, it will take some time to get the desired traction force. Exactly how the powertrain reacts to the downshift depends a lot on what type of gearbox is used. In a manual transmission or an automated manual transmission, the clutch must be opened during the gear shift, and then the vehicle will coast for about a half to 1 second during the gear shift. First, when the clutch is closed again, the engine torque is ramped up. This type of gearbox leads to a time without any traction force during the gear shift. Many automatic transmissions can shift gear while still providing all or some traction force, but even for them there will be a delayed response, as the engine will need to use a part of its torque to increase the engine speed before it can deliver full torque on the new gear. So to a request for higher force, an automatic transmission will also respond in a way that takes some time before the requested force is supplied. This is the running resistance curve for the vehicle in our example. While driving at constant speed on a flat road, the operating point will be somewhere along the running resistance curve. We can see that gear 5 will be used between 50 and 200 km per hour when driving at constant speed on a flat road. So how much acceleration can the powertrain provide without shifting down if the driver needs to accelerate a little just because the speed of the traffic increases a little? Here we have zoomed in on the force speed diagram. We can see how much net force the powertrain can provide on fifth gear. By dividing the net force with the vehicle mass, we get the maximum acceleration on the fifth gear on a flat road. At 50 km per hour, this maximum net force is available, providing 0.75 meters per second square acceleration. At 100 km per hour, the vehicle can accelerate 0.69 and 0.37 at 150. At 200, there is only a tiny 0.02 meters per second square acceleration. So these are the values for uncompromised acceleration. Should more acceleration be needed, the gearbox must shift down, and then it takes longer time until the vehicle is ready to accelerate further. In traffic which flows very smoothly, these acceleration levels will often be sufficient to follow the traffic flow without having downshift each time the speed goes up. In a little more aggressive traffic, rather frequent gear shifts can be expected, as the speed of the traffic goes up and down more rapidly. How could we improve this situation? The gear shift strategy in this figure would be the extreme opposite. It is not a strategy which would be used in a real vehicle, but it's useful for illustrating how selecting lower gears can provide higher acceleration without requiring gear shifts. In this strategy, the powertrain always uses the lowest possible gear. Note that it shifts up only when the engine speed on one gear reaches the maximum engine speed. This strategy would always minimize the engine torque and maximize the engine speed, which from fuel efficiency and noise perspective is a very poor strategy. Interestingly, we can see that the fifth gear is never used with this strategy, since the fourth gear is capable of running the vehicle even at its top speed. This is, by the way, typical for modern transmissions. The highest gears are not added in order to manage high speeds. They are there to get better fuel economy. If we again assume the vehicle is driving on a flat road, and then suddenly the driver wants to accelerate. How much acceleration can we get with this gear shift strategy without shifting down? At 50 km per hour, we get this net force, which can provide 5.5 meters per second square acceleration. At 100, we get 2.6. At 150, 1.3. And at 200, we get 0.4 meter per second square. This can be compared to 0.7 to 0.02 meters per second square for the other gear shift strategy. Note that there is never any downshift necessary, since this strategy always has the lowest possible gear. The powertrain can always provide its maximum traction force without any downshift. The desire to get a quick response to traction force request is influencing the design of real gear shift strategies, but keeping the fuel consumption low is often an even more important factor nowadays. This lecture has showed that quick response to traction force request is one reason to not always use the most fuel-efficient gear. In this course, we will mostly assume the most efficient gear to be used, but it is good to know that real gear shift strategies sometimes sacrifice fuel consumption to get a quicker powertrain response. Now test what you know about acceleration response on different gears in the exercises.